Okay, on K12 or K13 here, we have 85 grams of O2. It's held at a constant temperature. If the original pressure was 1 atmosphere, what would the pressure be if the volume is reduced by 40%? And then, what was the original volume? And so this would be a good one here to practice as well. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so O2 is 32U. So in this case with moles, we're dealing with 32 grams for 1 mole. So in this case, we have 85 grams of O2. So the grams to mole conversion here, right? We know that we have for 32 grams of it, that's 1 mole. And so the total amount of moles of gas was 2.66 moles. And then from there, we have the pressure, 101 pascals, one atmosphere. We can look at the gas beforehand, gas afterwards. And the number of moles is staying the same. The ideal gas constant's the same. The temperature stays the same. And then in this case here, it says that the volume is reduced by 40%. So in other words, volume 2 is only 60% of what it was. So 0.6 of volume 2. So when we do that, we can get the ratio of 0.6 of that. And so the pressure would be that value there. And then from there, we can find the original volume. That would be pressure 2. The original pressure is 101,000 pascals. And we have our other values there with moles. And so the original volume is 0.05978 meters cubed. Okay, so, when we eliminate what we have before and after, that can be really helpful for us. The temperature stays the same, and the gas, the amount of gas is the same, R is the same, we got that, right? Pressure, volume's the same, number of moles, we can actually compare with temperature too, volume's the same, pressure and temperature we can compare, etc. And so it's good to keep everything out there starting out. So pressure 1, volume 1 over nRT1, right? And then pressure 2, volume 2, and RT2. And in fact, you could have N1, N2, right, if the number of moles changes. And so, looking at the ideal gas before, the ideal gas afterwards, we've had a lot of practice with that, but it's good practice, to be using that, so it's good. Now, the number of molecules, right, is in a mole is Avogadro's number, 6.02 times 10 to the negative, or 10 to the 23rd. And so in other words, in this is a mole, right? This is the container that we have it, and then we have all of these. That's a lot of molecules, right? That's a lot of these things in there, and that's what that represents. And so to go back and forth between the number of moles and the number of molecules, if we take the number of moles and multiply that by Avogadro's constant, that'll give us the total number of molecules, all those dots inside there, which can sometimes be a lot, right? And so if we take a look at this situation with K14, we have 2 moles of O2, oxygen in a container. How many individual molecules of O2 does that correspond to? So you can do that, and then why don't you do that first, and then we'll move to the second part. So go ahead and pause the clip and try that first. All right, so 1 mole is this many molecules, so that's how many molecules that we have. And then for part 2, if a gas is at STP and volume is fixed, what will be the pressure if the temperature is increased by 85 degrees Celsius? So yeah, why don't you go ahead and try this one. Go ahead and pause the clip and give this one a shot. And when you're ready to check, you can hit play to continue. All right, so pressure, standard atmospheric pressure, 101,000 pascals. Temperature is 273 Kelvin. And that's temperature 1. Temperature 2 is 85 degrees Celsius higher, 358 Kelvin. And then volume 1 is equal to volume 2. We could set up our ratio between, our equation, the ideal gas before should equal the ideal gas afterwards. Volume's the same for both sides. Number of moles is the same for both sides. R is the same for both sides. And we end up getting, again, this ratio between the pressure and temperatures. And so pressure 1 over temperature 1 equals pressure 2 over temperature 2. We set that up so pressure 2 should come out to be 132,446.9 pascals. So if we look at the ideal gas law in terms of number of molecules, we can rewrite the gas law using N, capital N is the number of molecules, and then K, therefore, would have to be R divided by Avogadro's constant to give us a joule per Kelvin, which would then take care of the units there, right? Just like we had R instead of K in the last one, we had number of moles times R. This would be capital N number of molecules times K. So just a different way, if you're given number of molecules, you can use this as well. And this is Boltzmann's constant K. So K15, for the amount of water molecules found in the last problem, find the pressure of the gas if the temperature is 285 Kelvin and the volume of the container is 449 centimeters cubed. So we were dealing with 2 moles in that last problem, so that's that many molecules. And so now we can set up, this here. So go ahead and pause the clip and try this, and then when you're ready to check, you can hit play to continue. Okay, so in terms of the volume, we need to get that in meters cubed, so we cube the conversion. We should get 4.49 times 10 to the negative 4th meters cubed. We can place that in there and we'll end up getting pressure of, let's see, this would be 10,546,396.44 pascals. So we mentioned earlier the connection between kinetic energy and temperature. And so if we had a container and we had our molecules or whatever inside, okay, and they're moving around, the higher the kinetic energy, right, the higher the kinetic energy, the higher 1/2 mv squared they have. 1/2 mv squared. Wow, there we go. The greater the temperature that they're going to have, right? So to calculate that relationship, we're assuming a few things here. We're assuming that a large number of molecules is moving in random directions with a variety of speeds. The molecules are far apart on average, and they obey the laws of classical mechanics and interact only when colliding. And then that the collisions are elastic collisions when they hit. And so if we assume that, we can, produce some predictions and calculations here with what's going on. And so in SOCOS, in your SOCOS book, there's the derivation for this. You don't need this for our exam. But the average kinetic energy is, we know equal 1/2 mv average speed squared. And this will actually be equal to 3/2 kT, Boltzmann's constant, times the temperature itself. And that will give us the actual temperature, average kinetic energy of the substance. And it's directly proportional to that. So if we actually rearrange and then calculate this, and we incorporate mass, this is what we get. So we have the temperature in Kelvin here. We have the mass in kilograms. And we can figure out the root mean squared speed, the average speed of the substance. And so that's pretty neat, because if we know the temperature of the substance, we can have an idea of how fast the average molecule is actually moving, and that can be pretty cool here. So let's do that. Let's say that we have, well, here's 1 U, or atomic unit, is 1.66 times 10 to the negative 27th kilograms. I'll find the average speed of 10 molecules of O2 in a closed container if the temperature is 10 degrees Celsius. So this is more just kind of practice using these numbers. How realistic this is may not be so realistic. That's okay. But we can go ahead and practice this. So go ahead and pause the clip and give that a try. And yeah, when you're ready to check, you can hit play to continue. All right, so the atomic mass is 32 U, and we have 10 molecules of that. And so you know, 320U, which we can get into kilograms. And then when we use that equation, we should get 148.5 meters per second. Hopefully remember the 10 degrees Celsius would be in Kelvin, so that'd be 283 Kelvin. And you've got the mass in kilograms. Then you've got K constant. And so you should get an average speed of 148.5 meters per second. Okay, so let's say we have 2 moles of fluorine gas in a closed container of 1 liter at 1 atmosphere. Find the root mean squared velocity of the particles in the container. So go ahead and pause the clip and try this, and then when you're ready to check, you can hit play to continue. All right, so 1 liter is 1 times 10 to the negative third meters cubed. 1 atmosphere is 101,000 pascals. And we have 2 moles, which we'll need to get into how many kilograms. So if we know F2, fluorine gas, has 38U per molecule, right? So we have 38 grams in a mole of that. So we can get that into kilograms. We have 2 moles of it, so 76 kilograms, or 76 grams, you can get into kilograms. Place it into our root mean squared equals square root of 3kt over m, and we should end up getting for this a value of, yes, so in this case, right, we don't have, so we have mass, we don't know the temperature, right, so we have to figure out temperature. We can use the ideal gas law to do that, and when we place all our values in there, P equals nRT, if we wanted to do that, we would use the 2 moles for, you know, for N, 2 moles, temperature in Kelvin is what we're looking for, and then the pressure we have 101 pascals, 1,000 pascals, and then our volume we have is right here. So we should get this as the temperature. Once we have that, we should get a speed, average speed of 5.75 times 10 to the negative 11th meters per second. So you can probably tell that I just kind of made this up and put it together, but that's how fast it would be. And that's what we have there.